Think about the thermostat on your wall for a second. Have you ever wondered exactly how the physical heat in your room is instantly transformed into a crisp digital number on a screen? Welcome to the Explainer. Today, we're diving straight into the hidden architecture that constantly translates the physical world around us into digital, actionable data. It's this fascinating journey that happens in literally a fraction of a second, but it completely dictates how every single instrumentation system functions. Let's get into it. Here is our roadmap for today. First, what exactly is a measurement chain? Second, moving from physical to signal. Third, processing and taking action. And finally, the weakest link principle. Section 1. What is a measurement chain? Fundamentally, a measurement chain is the ordered sequence of physical and electronic transformations that a measurand undergoes. It goes from its raw origin in the physical world all the way to its final representation as meaningful, actionable information. You can kind of think of it as a highly sophisticated lightning-fast game of telephone, but instead of whispering words, we're continuously translating physical reality into digital instructions. Now, you'll often hear this referred to as a measurement loop or a signal chain, but honestly, the chain metaphor really hits the nail on the head here. Every single link has to perform its function reliably, or the message just doesn't survive the trip. The entire chain is essentially broken down into 6 sequential stages, moving from a physical quantity all the way through to actual actuation. And because this operates literally as a chain, a failure or honestly even just a slight degradation at any single link completely compromises the integrity of all the information that comes after it. You simply can't fix a broken link later in the chain. Once that data is corrupted, the final action is going to be compromised. There's no way around it. Section 2. From physical to signal. We're going to look really closely at these first 3 stages: sensing, signal conditioning, and signal transmission. These are the absolutely crucial initial steps that bridge physical reality with the electronic domain. They capture the raw environment and prep it for a high-speed journey.
It all kicks off at stage 1, sensing. This is where the physical quantity of interest, what we call the measurand, actually interacts with a sensing element. And thanks to a known physical law, this interaction produces a primary signal. Whether it's ambient temperature interacting with a thermocouple or fluid pressure hitting a superdelicate membrane, this is the exact moment reality is captured. It's literally where the physical universe shakes hands with the electronic one.
But here's the catch. That primary signal is rarely ready to be used as is. It might be incredibly weak or completely distorted by background interference, so we have to condition the signal. It might need amplification to boost a really faint pulse, filtering to strip out all that messy background noise, linearization to straighten out its response curve, or even conversion into an entirely different electrical format. This stage is absolutely vital to ensure the signal is robust and standardized for the journey ahead. Once your signal is cleaned up and perfectly conditioned, well, it needs to travel. That's stage 3, signal transmission. It's simply the act of quickly conveying that conditioned signal from the point of measurement to wherever it's going to be processed or displayed. As you can imagine, depending on the environment, this rapid transport can happen over traditional wired connections, spanning a massive factory floor, or through modern wireless means just bouncing right through the air. Section 3. Processing and taking action. Now we are fully entering the digital realm with the final 3 stages of our chain: signal processing, data presentation, and actuation. Let's see exactly how that transmitted signal is interpreted, viewed, and ultimately used to change the physical world. At stage 4, we hit signal processing, and things start moving incredibly fast. Deep inside microcontrollers and processors, the transmitted signal is interpreted. It gets scaled to the right proportions, corrected for any lingering environmental errors, and integrated with other incoming signals. This rapid, continuous processing is what actually takes a raw transmitted voltage and turns it into derived, meaningful quantities that an automated system can understand and use to make real-time decisions. Then we reach stage 5, data presentation. After all that invisible electronic travel and high-speed calculation, this is where the data finally meets human eyes. The processed info gets displayed on monitors, so operators can actually read it. It's stored in databases for historical records and trending, or it's communicated straight up the chain to broader, facility-wide data management platforms. And finally, the whole shebang wraps up with stage 6, actuation, where applicable, of course. This is the culmination of the entire journey. The information derived from the measurement chain is now used to drive physical corrective actions through actuators. Whether that's spinning up a heavy industrial motor, adjusting a massive flow valve, or simply your smart thermostat clicking the AC on, this stage completes a closed control loop. Our initial physical measurement has successfully driven a calculated physical action. Pretty cool, right? Section 4. The weakest link principle. To truly understand how to build or even just troubleshoot these systems, we have to look at the characteristics that define every single stage of our chain. Each individual component introduces its own static and dynamic traits that directly affect the final measurement's fidelity. Static characteristics measure the system at rest, so things like its overall accuracy, resolution, and maximum range. But dynamic characteristics? Those measure how the system responds to a changing, real-time environment, like its bandwidth or phase shift. Essentially, it boils down to how quickly and cleanly can this setup react to sudden fluctuations. And that brings us to a fundamental, absolute core principle of measurement chain design. Overall system performance is bounded by the weakest element. Think back to that literal chain metaphor we talked about earlier. It absolutely does not matter how robust and expensive 5 of your links are if the 6th one is made of weak, brittle plastic. The entire chain is going to snap at that exact point. Let's look at this in the real world. Say a system architect pairs a highly expensive, top-tier accuracy sensor at stage 1 with the cheap, low-resolution analog-to-digital converter during stage 2. The result? Well, the overall system accuracy will be strictly limited by that low-resolution converter. It completely negates the high-accuracy sensor. It's a total waste of the sensor's capabilities. System architects absolutely must ensure that the performance specifications of all components are mutually consistent and perfectly matched for the intended application. Which leaves us with this final, vital thought. As you look at the complex systems operating all around you, or perhaps the ones you're designing yourself right now, ask yourself, if your system fails, do you actually know where your weakest link is? Because truly understanding the complete journey of a signal means knowing exactly where it's most likely to break. Thanks for joining me on this explainer. Keep learning, and we'll see you next time.